So, Sydney, you weren't with us today, I think, in lecture, but I got this new fancy device, which I really like. Okay, so for the quiz on stoichiometry, right? So let's just go through question by question. Now there's a lot of different versions of these questions, so if they don't match exactly what you guys had in your problems, the way that we're solving them should still work, right? The other thing that I wanted to point out is we can do some stoichiometry in the context of gas law problems as well, because I think that's something that I've seen students having a lot of anxiety about, right? Is I already don't understand the stoichiometry, and now you're adding another layer, right? So, if it's okay with you guys, I think we could go through these problems and then maybe one more. Would that be all right? Cool.
Yes, please.
All right. So I have that first question on the quiz was basically about a recipe. Different recipes, different amounts, but the idea is that it was a limiting reactant type of problem, okay? So when thinking about solving this problem, what we're trying to figure out is which ingredient which is our code here for a reactant, right, is limiting the amount of product we can make. Okay? So, the one that I'm looking at has a recipe for a turkey sandwich, and it has 2.9 ounces of turkey plus 2 slices of bread goes to 1 Sammy, right? And the information that we're given is that we have 25 ounces of turkey and 19 slices of bread. Whoops. Oh my God. And we want to know how many sandwiches can we make? Okay. So, in thinking about this as being a limiting reagent problem, we have 2 ingredients, right? And we have X amount of each one of those ingredients. So what we want to do is figure out how to turn those into sandwiches, right? So if I have 25 ounces of turkey, and I know that each sandwich requires 2.9 ounces of turkey, I can put 2.9 ounces of turkey down here, right? Will give me 1 sandwich. Does that make sense, guys? So, I'm going to ask you guys to be my calculators because my phone is not normally my calculator. So if we do the math here, we have 25 divided by 2.9.
8.62.
8.6 sandwiches, right? And the problem tells you specifically to assume that you can only make whole numbers of things, right? So this would round down to 8 sandwiches, right? Does that make sense?
Yes.
Cool. So now we have to see how many sandwiches we can make with our slices of bread. Oh my gosh, I cannot spell today, you guys. Slices. So I know that I need 2 slices of bread for every 1 sandwich I make. So I've got 2 slices for 1 Sammy, right?
So it'll be 9.5, but you want to run it down to 9.
Exactly. Right? So, if we're looking at who is limiting the number of sandwiches, right? What ingredient is limiting here?
The turkey.
The turkey. Does that make sense, Sydney?
Yeah.
You comfortable with that? So whichever ingredient makes the least amount of product, that's the maximum amount of product that we can make, right? So that's what this problem was trying to get at, right? I think one of the things that's probably frustrating for students about me is that you can learn how to do a stoichiometry problem but still not understand stoichiometry, right? So what I saw is a lot of people were able to solve the last 2 questions but couldn't figure out how to do this problem, right? And for me, knowing how to do this problem is equivalent to understanding how to do it in chemistry, right? They're not different things, they're just 2 different kinds of problems, right? So some people find this to be much more intuitive and it makes more sense because I make sandwiches and I get sandwiches. But some people find it frustrating because they're like, what the frick does sandwiches have to do with chemistry, right? So, but I love these kinds of questions because I think they really test whether or not you understand the concepts that are going into it, right? So this kind of limiting reagent problem, may not be the one that you see on an exam. There may be one that's chemistry based, but the concept and the way that you solve the problem is exactly the same, right? You have your balanced chemical equation, aka your recipe. You have the amount of each reactant, which you have to convert into product. Whichever one makes the least amount of product, that's your limiting, right? Any other questions about those guys?
It makes a lot.
Yeah.
Cool.
I was going through your fish tacos video the day we talked. I was just a little confused on how you
Yeah, totally. And I think that's kind of one of the hard things is if you weren't in a lecture, you might be like, why is she talking about this, right?
because we can't ask the question.
Totally. You're like, where did this come from? But I think that the recipe analogy is really helpful for understanding why there always has to be a limiting ingredient. Does that make sense?
Yeah,
cool.
It does.
All right.
I just have to grab my charger.
No problem. Is it okay if I erase this problem, you guys?
Yeah.
Cool.
Yeah, that's fine.
All right. So now, this next problem from the quiz is probably going to be a little bit harder to relate if you had a different question because there were a lot of variations on this question. But the one that I have here is reacting aluminum solid with aluminum solid with hydrochloric acid to form aluminum chloride and hydrogen What am I doing? Oh my gosh, sorry you guys. Let me try this again. All right. This was aluminum solid reacting with zinc chloride. There it is. Sorry about that, you guys. And that was forming aluminum chloride. Oops. All right, you guys, I'm really messing this up. I'm sorry. I'm going to try and write it down correctly this time. 2 aluminum solid. And did either of you guys have this problem for the second one?
I didn't have this.
Not too sure.
Okay.
I know I saw something similar to it, but I can't remember.
Cool.
I think it was with sodium instead.
Cool. Okay, and the problem has 3.5 grams of aluminum reacting with zinc chloride. And it's asking what mass of zinc chloride is required to react with this mass of aluminum. Okay? So, looking at this problem, the first thing I want to do is figure out what unit I'm trying to get to, right? So what is the unit that I'm looking for? Or what is the quantity that I'm looking for here? Grams of
Zinc chloride.
Yep, exactly. So I'm trying to get 2 grams of zinc chloride, right? And I'm starting at grams of aluminum, right? So I'm going to show you guys, this is the way I like to build a map before I start doing any of the stoichiometry, okay? So if I'm starting off with grams of this guy, right? Thinking of the molar coaster, right? What is my first move to get out of grams and into moles? What do I need?
The molar mass.
I need the molar mass, right? So anytime you see that you're starting in grams, immediately you should be thinking, I need to get to moles, right? Because grams of one thing can't talk to grams of another thing, right? The only thing that can talk to each other is moles and moles, okay? So we're thinking I need to get to moles of aluminum, and for that I need the molar mass of aluminum, right? Aluminum. Sorry, guys. Does that make sense?
Yes.
So now if I'm at moles of aluminum, what's the next thing that I want to go to?
The molecules.
Don't need to go to molecules here.
Oh,
right?
2 grams.
Can I go straight to grams of zinc chloride here?
Just the moles of zinc chloride.
Right. So I need to get to moles of zinc chloride. Does that make sense, guys? Cool. And what piece of information can get me from moles of aluminum to moles of zinc?
Is it molar mass still?
No, so now instead of going on the molar coaster from grams to moles, right? Now we're going from moles to moles, right? What piece of information do we need to go from moles of one thing to moles of another thing?
All I can think of is avocado's number. But
So avocado's number is really only when you're dealing with molecules or atoms, right? So in this case, we're not getting into any molecules or atoms. The only thing that we're working with is grams and moles, right? So that means the only thing we're going to need in terms of tools are molar masses, and then this other thing, which is going to be molar ratio. Okay, so when we're looking at going from moles of one thing to moles of another, there's two places that we can get that molar ratio from, right? Molar ratio. So the molar ratio can come from the chemical formula or the empirical formula, right? That's one place.
Is it
But
the charge?
it's not the charge, no. But in the case that we're looking at a chemical reaction, the molar ratio is going to come from the balanced chemical equation, okay? So this is where we're going to get the molar ratio, right? Specifically, we see that we have 2 moles of aluminum, right, for every 3 moles of zinc chloride. Does that make sense? So going from moles of this guy, we need 2 moles of this guy for every 3 moles of this guy, right? And then what's the last step?
2 grams.
The
And
molar mass.
And we need the molar mass for that, exactly, right? So we'll need the molar mass of zinc chloride, right? So you guys see how building this map first gives you a little bit more to stand on, right? It's not necessarily easier or harder, but it gives you a plan, right? The hardest thing is figuring out what you need to make each one of these jumps, right? And this is that one step that takes us from doing molar conversions with just the molar coaster to using this balanced chemical equation. Does that make sense? And that's really what takes molar conversions and brings them into stoichiometry, is this balanced chemical equation gives us the molar ratio here. Okay, so now we can just set it up. So we have 3.56 grams of aluminum. And we want to go to moles of aluminum. So if I want moles of aluminum on top, I'm going to want grams of aluminum on bottom. And where do I get the molar mass of aluminum?
On the period.
Periodic.
Yeah, exactly. So
So
I've got,
it's 107.87.
ooh.
Oh wait, sorry, I'm looking at AG.
I
Aluminum.
was like, that's an A, but it's not the right A. 26.98.
982. Do you have to round it out, or do you have to put like the thousands place also?
I don't care.
Okay.
I don't care. I would give you the answer. It would be correct either way. So, yeah. So this will cancel out my grams of aluminum here. And then going from moles of aluminum, right? I want to get to moles of zinc chloride. So that means I want moles of aluminum down here, so they'll cancel. And I want moles of zinc chloride up top, right? And specifically, we know that there's 2 moles of aluminum for every 3 moles of zinc chloride. Right? So moles of aluminum will cancel with moles of aluminum. And now we just need to make this last step from moles of zinc chloride to grams of zinc chloride, right? So here we'd need the molar mass of zinc, which is 65.38, plus the mass of chloride times 2.
It is 136.28.
Right, so we have 136.28 grams on top per 1 mole on bottom. And so my moles of zinc chloride will cancel there. And now I just have to do the math.
I got 20. Oh, let me double check. 26.97.
That sounds reasonable to me. 3 times.
I like wrote it all out, so that's why it's taking me.
No worries. Twenty-six point.
Oh.
Is
I
that?
got 26.973.
That's what I got too. Right? So does it make sense how we set that problem up, guys?
It does.
Cool.
Is that how all stoichiometry questions are gonna be, or are there different variations?
There's different variations. And that's, I think, what students find frustrating, right? Is it would be really easy if every problem was like this, you just plug in the different numbers, right? But that's not how this works, right? What we have are a bunch of different types of questions that we could ask, right? Here we were asking about how much of a reactant we'd need to react with some mass of the other reactant, right? We could be asking if we have this much aluminum, how much zinc would be formed, right? Assuming that we had excess zinc chloride. We could be asking if we had this much zinc product made, how much aluminum, what must we have started with, right? So do you see how the permutations of the questions are really very numerous, right? The ways that I can ask this question are varied, and there's a lot of them. But the way that we go about problem solving is the same, right? That's why I think not starting here, but starting here is the best way to plan a strategy for problem solving. Does that make sense?
It does.
Yeah.
Cool. Okay, so I want to do, if it's okay with you guys, I'm going to do one more of those problem number 2 types, because I think most people were comfortable with the third problem, which I thought was going to be the hardest, but everybody seemed to do really well on that one. So, okay. And this is kind of similar. So this is another version of question 2, which was looking at propane C3H8. And I'm going to write this down for you guys. Can I erase? Is that all right?
Mm-hmm.
Cool.
Yes.
So we have this guy, which is propane, is being reacted with oxygen gas in a combustion reaction to form carbon dioxide and water vapor. You guys recognize this one?
Yeah, I'm
Okay.
actually looking at the quiz right now.
Cool, cool, cool.
Yeah.
Aaron, anything familiar here?
I remember seeing a video of you talking about combustion.
Cool.
Yeah, instead of the propane, it's fuel.
Cool, cool, cool. So we're doing a combustion reaction here, and we're given that we have 15.4 kilograms of propane, right? And we want to know what mass in kilograms of CO2 is formed. And it says that you can assume that there's excess oxygen from the air, okay? So we're assuming excess O2, right? So why is it important that that second part is put in there? Why is it important to know that oxygen is in excess?
Is it because that's what makes it a combustion reaction?
Not quite. I mean, definitely having oxygen is a requisite for making this be a combustion reaction. But what we're saying when we say assume excess O2 is that our limiting reagent is propane. Does that make sense?
Can you explain how again?
Yeah, absolutely. So if we know that we have excess O2, right?
Okay.
What that means is that we have more than enough to react all of this propane, right?
Yeah, now I get it.
Which kind of makes sense too, because if you're doing a reaction, if you're burning something outside in open air, right, then there's plenty of oxygen in the open air to make this reaction go, right? And we kind of know that intuitively. So that's a really common assumption that you make with a combustion reaction, because usually combustion reactions are taking place in open air, which means there's plenty of oxygen. There's no limiting oxygen there, right? But does that make sense in terms of why that part of the problem is there?
Yeah.
Cool. Yeah, because without that, you wouldn't be able to assume that all of this is going to react. Okay? Cool. So the next thing we want to do is set up our roadmap. Right? So here we're starting off with kilograms of carbon dioxide, right? So what's the first thing that we should be thinking to do with our kilograms of carbon dioxide?
Converting it to grams.
Exactly, right? So I want to get out of kilograms and into grams of CO2, right? In which case I need the conversion factor that goes 1 kilogram is equal to 1,000 grams, right? Does that make sense, guys?
Is this information we should already know prior to the exams?
Yes,
Okay.
but I mean, so this is one of the things that I ask you guys to memorize at the beginning of the semester. But since you guys are doing all of this stuff online anyways, you could definitely just have a crib sheet with all of the conversion factors on it. The most important thing is knowing how to use them, right? So what would the next step be?
It was the molar mass, right?
Yeah, so we want to get to moles of carbon dioxide. I'm sorry. Why am I starting with carbon dioxide, you guys? You guys didn't stop me. You're like, yeah, sure, that's what we want to do.
I was wondering why it wasn't propane.
Sorry, you guys. That should be propane. Yeah. That's not cute, but at least we fixed it before I got through the entire problem. Okay, so we want to get to moles of propane. There we go. C3. Ay. And for that we need the molar mass of propane. What next?
We go to moles of CO2.
Exactly. There we go. Now we got CO2. And how do we get from moles of propane to moles of CO2?
The mole ratio.
Yes. So for every one of the propane, how many carbon dioxides do I have?
3.
Exactly. 1 mole of this guy for every 3 moles of carbon dioxide. And since I ran out of room, just do one of these. So from moles of carbon dioxide, what's the next step?
Finding the molar mass of carbon dioxide.
Right, so we can get to grams of carbon dioxide, exactly. Yes. Both of you guys got it. So we got grams of carbon dioxide is where we're trying to go. And to get there, we need the molar mass of CO2, right? And then are we done?
No, there's one more step.
Yeah, so we were asked to get to kilograms, right? So here we know we need kilograms of CO2, which means that we need to use this factor again. Now, ideally, if you guys were doing this on a piece of paper, you would be able to do it long form instead of having these confusing arrows. But hopefully this is still helpful for you guys building this map.
It is.
Cool.
Very helpful.
Cool. So we're starting off with 15.4 kilograms of propane, not carbon dioxide. And our first step is to go from kilograms to grams, right? So should kilograms go on the top or the bottom?
On the bottom.
On the bottom, exactly. So we have 1 kilogram gives us 1,000 grams.
And that's... I'm just confused.
Why?
Why the... Because I thought it was going to be on the bottom 1 kilogram of the propane.
Sorry, say that again?
Oh, is it going to be still... Okay, it's still 1 kilogram of propane on the
yes,
bottom.
so basically this is the factor we're using, right? And what you want to be able to know is, do I put the 1 on bottom or the 1 on top, right? But we know that 1 belongs to kilograms, right? And we know that kilograms needs to go on the bottom to cancel kilograms up top here, right?
Oh, okay.
Does that make sense? So that's our motivation for why we put kilograms on the bottom, because we want that to cancel out so we can get to grams of propane.
Okay.
Cool. So what's the next step?
I want to put grams on the bottom.
So we want to get grams of propane on the bottom. And what unit are we trying to get to?
Moles.
Moles, absolutely. So here's where we're going to need the molar mass of propane. That's 12.011. Sorry, you guys. It's really ugly.
44.097.
Awesome. So that number belongs to grams, right? Because the molar mass is always some number of grams per 1 mole of the compound, right? So we've got 44.01 because I'm lazy and I don't have space.
Would it be 44.1?
Oh my god, thank you. I'll just make a blob there. That makes it more intelligible, right? So now grams of this guy will cancel with grams of that guy. And now what's the next step?
You're going to put the mole of propane on the bottom, which is 1.
Mm-hmm.
And then the molar ratio for carbon dioxide, which is 3 on
3
top.
on top. So now moles of this guy will cancel with moles of this guy. And now I gotta come down here, start another line. So now I have moles of carbon dioxide. What's my next step?
So you're going to place that on the bottom, and then you're going to try to find the molar mass of carbon dioxide.
So for every 1 mole of carbon dioxide, there's 44.01 grams of carbon dioxide. So now moles of CO2 up here will cancel with moles of CO2 here. Sorry, I didn't write my CO2 in there. And now what's my last step?
Converting grams to kilograms.
Exactly. So now here we have 1,000 grams of CO2 for every 1, oops, not mole, excuse me, kilogram of CO2. So this would be a little bit easier to see if it were all on one line. But hopefully you guys can see that 1,000 grams is on top here. And 1,000 grams is on bottom here, right? So I'm thinking get rid of it, right? You guys picking up what I'm laying down?
Yeah.
So goodbye. Goodbye. So now I have 15.4 times 3 times 44.01, and all of that being divided by 44.1.
I think I did my math wrong.
What'd you get?
46,200.
Yeah.
Why did you take away the or like scribble out the 1 kilogram over the 1,000 grams of CO2, like the very last one?
Here we have 1,000 grams on the top, aka in the numerator, and 1,000 grams in the denominator.
Okay, that's
right?
where I took out the 1 and the 1,000, but then I left an additional 1,000
Gotcha.
numerator. So really it'd be like 46.
Yes.
1, 2.
Cool.
Something along that.
I got 46.1.
Cool. 46.1, 46.2. We're all in the ballpark. Right? And if you weren't sure, right, one of the other things that I can see just by looking at this is I have a molar mass of 44 here on the top in the numerator, and then another molar mass of almost exactly the same thing in the bottom in the denominator, right? So really all I kind of need to put in my calculator is 15.4 times 3.
Oh my goodness.
Does this make sense for you guys though?
It does.
Mm-hmm.
Cool. Any questions about how we got there? Now, one of the other things that I wanted to mention is I tend to like to do problems all in one line because I'm lazy and I don't want to do a bunch of calculations. But I think a lot of students feel much more comfortable doing one step at a time, right? So doing this 15.4 times 1,000, getting an answer, and then making that answer the place that you start with the next step, right? So literally just doing this calculation and then using that number to do this calculation and then using that number to do this calculation, right? And if that's more comfortable for you, by all means do it that way, right? That's completely fine. The main reason why I like to do this way is because I'm so lazy and I can see things like, oh, 1,000 on top, 1,000 on bottom, get rid of that, right? Whereas if you were to do this out stepwise, you'd end up doing all of those steps, right? But again, I want you guys to use whatever technique makes most sense to you and gets you there correctly, right? So if it's easier to do piece by piece, do it that way. That's totally fine. Okay?
This helped a lot.
Awesome. Okay, so I'm gonna try and wing it with a question about gas stoichiometry. So let's say I have magnesium solid reacting with hydrochloric acid to form magnesium chloride and hydrogen gas. Let's say I want to know how much, meaning what volume, of hydrogen gas will be produced by reacting 3.5 grams of magnesium with excess hydrochloric acid. My handwriting got kind of crappy there. Can you guys read all of that?
It's legible.
Cool. So, first things first, what does excess HCl mean in this reaction?
That it's not that the it's not the limiting.
Yes,
reaction.
exactly, Sydney. Yay, you're doing it. I love it. So, what is the limiting reagent here, or the limiting reactant?
The magnesium.
The magnesium, exactly, right? So knowing that magnesium is our limiting reagent, right, we can assume that all of this magnesium was reacted to form hydrogen gas, right? So what we're looking for in this problem is a volume of H2, right? So that's where we're trying to go. And we're starting with a mass of magnesium, right? So, what are we thinking our first step should be?
Molar mass.
Molar mass, absolutely. So if we want to get to moles of magnesium, we need the molar mass for magnesium, right? What about the next step?
The molar ratio
Mhm.
to hydrogen.
Yep, so we want to know, going from moles of magnesium, how do we get to moles of hydrogen gas? Oh. This is important. I forgot this on the homework too, but this is very necessary information. At STPs is at standard temperature and pressure, and we'll talk about what that means in just a second. But going from moles of magnesium to hydrogen gas, right? What's my molar ratio?
1 to 2. Oh, sorry. 1 to... Oh, 1 and 1.
1 and 1, exactly, right? So for every 1 mole of magnesium, I have 1 mole of H2 gas, right? So, now I've got moles of something, and I want to get to liters of that thing, right? So, I think Erin was there this morning, Sydney, you weren't, but one of the new problems that we've introduced is dealing with solution stoichiometry, okay? So, seeing moles and wanting to go to liters could make you think, oh, maybe I need a molarity, right? You don't know what that means, Sydney? That's okay. You're going to watch the video later. But here we're thinking, oh wait, H2 is a gas, right? So if I want to go from moles of a gas to a volume of gas, right? That's an indication that I need the ideal gas law. Okay? Does that make sense?
Kind of.
So, this is our ideal gas law, right? PV equals nRT. And I know that I can relate the number of moles of a gas to the volume of a gas using this equation. Okay? Now, what we're not sure about is what the pressure is and what the temperature is, right? So, that's where this standard temperature and pressure comes into play, okay? So STP is the standard temperature and pressure. The standard temperature is 273.2 Kelvin, which is also 0 degrees Celsius, right? But when we're working with PV equals nRT, we never work in Celsius, right? We always have to convert out of Celsius into Kelvin. So might as well just start in Kelvin here, right? And the standard pressure is going to be 1 atm, 1 atmosphere, okay? So, now let's start trying to get our steps down, okay? So, starting out with grams of magnesium. Right? Our first step is going to be to use the molar mass of magnesium. So looking at the periodic table, we have 24.305 grams of magnesium for every 1 mole of magnesium. What should I put next?
The molar ratio.
Yeah. So what do I want on bottom?
1.
1 mole of
1 mole of magnesium.
Magnesium goes on the bottom, and 1 mole of hydrogen gas up top. So what does that give me?
When you add all of it together so far? Or?
So we've got 3.5 divided by 24.305.
So it's 0.144. The others are zeros.
Perfect. Sorry. There we go. And what variable does that represent in our PV equals nRT?
Can you repeat that one more time?
Yeah, so in our ideal gas law, right, which variable is this?
Is it N?
It's N, right? You okay with that, Sydney?
Yeah.
Cool. So this is going to be our N value, right? Now, if we're looking for volume, we need to rearrange PV equals nRT to solve for the volume, right? So how do we get volume by itself?
I feel like this was a question during the beginning of the semester.
I know, right? Stupid algebra.
Is it something with density times mass? Or...
Nope, you guys are making it too complicated. Too complicated. So if I want volume by itself, right, I need to divide both sides of the equation by P?
P and N?
Just P?
Just P.
So if I divide both sides by P, P goes away here, and I'm left with just volume on this side. That's what I mean by getting volume alone. Does that make sense, guys?
Yeah.
So I'm going to rewrite that over here. So volume is equal to nRT divided by P. Does that make sense, guys?
Mm-hmm.
Cool. So now, here, we can start plugging things in, right? We have 0.144 moles of H2. The R value is always going to be this guy, which I don't have enough room to write the units, but you guys hopefully know. And then 273.
What is the R unit exactly?
The R unit is liters times atmospheres divided by moles Kelvin.
And it's always the same number, right?
Yep, totes. And all of that will be divided by 1 atmosphere. So the reason why we need everything to be in the right units is so that our R value, everything in the units will cancel out and we'll just be left with liters. Does that make sense? So we have ATMs are on the bottom, which means that ATMs will cancel with ATMs. We have moles on the top and moles on the bottom. Those guys cancel. We have Kelvin on the top and Kelvin on the bottom. Those guys cancel. So we just end up with liters.
I have 3.23.
3.23?
Yeah. Well, 3.228.
And you've got a 0 here after the decimal?
Yes. I'll like redo it just in case.
I'm not saying you're wrong. I made up these numbers.
Oh no.
So I honestly don't know.
You're totally fine. It's always good stuff, check. Yeah, well, without the decimal point in Kelvin, I have 3.2259.
Okay. Is that what you got, Sydney?
I am plugging it in right
Cool.
now. 3.2, yeah.
Cool. Awesome. So, questions about this question? What do you think?
Or I actually am just want to make sure I know what I'm doing for,
Totally.
like, once you get to the end of having it all plugged in.
Yep.
How do you know? Because you started canceling out stuff.
Mm-hmm.
And that's what I'm just confused about. Like,
so, in terms of canceling units, that would be much easier to do if I had more space, right? So if I had space next to this guy, I would write out the units next to it, and then it would be easier to see how I just canceled all those units. Does that make sense?
Yeah, but how is it like L times ATM over mole times K? Like, how do you know it's that?
That's just a part of the constant.
Oh, okay.
Yeah, so it's always going to be that, right?
Okay.
So R is always going to be 0.08206 liters times atmospheres divided by moles times Kelvin.
And do you use R for all gas problems?
Yep.
And then when we're canceling out? Okay.
Yep. Every single one, right?
Okay.
So anytime you're working with a gas and you want to get one of these other variables, right? Your thought process should automatically go to PV equals nRT, right? And even if there's steps that maybe go before that, right? Anytime we're trying to go from moles to liters of a gas or liters to moles of a gas, right? That should trigger this, oh, this is going to be a gas law problem. Okay? Does that help, Aaron?
It does.
But
It
again,
makes a lot more sense.
cool, awesome. That's what I love. So the one other thing that I wanted to mention is just to re-emphasize, and I know I've said this a million times in the last hour, but this roadmap is really, really helpful, I think. You guys agree?
It is, yeah. No, it helps a lot.
So, and I think there's a tendency as students want to just like dive in and get it done. But taking that extra minute to figure out a strategy for how you problem solve really makes it so much easier to do these problems. You know what I mean?
Mm-hmm.
So, so I really recommend doing the map before you start to try and solve the problem, because otherwise it can be really easy to get lost here, right?
And just, I feel like this might be a dumb question,
No,
but
not at all.
how when we're reading a question, how do we know that it's a gas stoichiometry versus just a regular, like what makes it gas?
So if we're looking for a volume of a gas, right, which H2 in this case is a gas, then we should be thinking PV equals nRT.
Okay.
Right? So if this is where we're trying to get, and it's a gas, then we're thinking, okay, we definitely need to use PV equals nRT, but we're going to have to start with a few steps that involve stoichiometry, right?
Mm-hmm.
Does that make sense?
Yeah, it is.
Cool. Aaron, do you have any other questions about this one?
Not at the moment.
Cool.
I think I'll like continue doing like some of the homework questions and watching the videos.
Yeah.
But if
So
there's any, I can always ask you.
absolutely. So so the one thing that I just wanted to mention again is the more of these practice problems you do, the more confident you're going to be going into the exam, right? So or into the quiz, which is coming a little before that, but yeah, so just try and do as many of those problems as you can. And honestly, especially for gas stoichiometry problems, if you only have a couple of those problems to do, see if you can do them one day and then come back and do them the next day, right? Do you get the right answer? Because honestly, if you're anything like me, you're going to forget by tomorrow how you did this problem, right? So just coming back and saying, okay, can I do that problem again? Do I get the same answer? And if the answer is yes, then that means that your methodology is working, right? And if the answer is yes, then that means that you could try another problem and you should still be able to get the right answer, right? It may be that you take a slightly different path, right? But that's okay. It's not about knowing every possible route to get everywhere. Do you know what I mean? Like that would be an overwhelming amount of information. We're not trying to figure out every single way to get to every single place. What we're trying to figure out is how do we strategize to problem solve, right? And that's something that we can do. We can do that in all different kinds of ways, and that's the flexibility that you really get from chemistry that you don't get from a lot of other areas, right? Whether you like it or not. So, cool. Any other questions about those guys? All right, I'm going to turn this off.